Let's talk about what a bond is. Why do atoms form bonds? Bonds form to make molecules more stable. A molecule will do anything it can to be as stable as possible, and if that means making a bond, then it will. If it means a bond makes it less stable, then it won't make a bond. But most common molecules that we are familiar with form because bonding makes molecules more stable. So what is a bond? A bond is an overlap of orbitals. What does that mean? In a previous video, we talked about what orbitals are. If you haven't watched that video, I've got a link down below. You're probably going to want to watch that video to make sense of this one, because I introduce a novel way of thinking about what an orbital is that maybe you're not familiar with. So how do orbitals overlap? Recall from that video that orbitals are the answer to a very complicated math equation. Complicated math equation that defines a volume of space within which it's probable to find an electron. On the one hand, a bond is an overlap of orbitals, but orbitals are answers to math equations. So how do we overlap math equations? That doesn't make a lot of sense. How do you overlap math equations? The way we do that is with a mathematical construct called the linear combination of atomic orbitals, LCAO. This is a set of mathematical rules. It's used in lots of contexts. Chemistry is just one context. It's a set of mathematical rules that allow us to combine, to overlap math equations to form orbitals. There are a couple of rules that go along with the LCAO. This is not meant to be a math lecture. I'm not going to dig into all the math behind linear combinations. But let's get to the practicalities. How do we use linear combination to do chemistry? One of the first rules that we have to abide by when we do linear combinations is that the number of equations that we start with has to be the same as the number of equations that we end with. And if the equations are orbitals, that means the number of orbitals that we start with has to be the same as the number of orbitals we end with. Another rule that we have to follow is in order to combine these math equations, we combine them both constructively and destructively, or another way of saying that is additively and subtractively. Doesn't make a lot of sense in words. So let's go through a little bit of a pictorial example, and then we'll talk about what bonds are. So bonds are orbitals, and orbitals are an equation that defines a volume of space within which it is probable to find an electron. If we want to form a bond, we need to take two orbitals containing electrons and combine them together. So let's think about electrons in that wave-particle duality. Are you familiar with this? Do you remember this? That electrons have that paradoxical duality of being both waves traveling through space and discrete particles. If we're going to form a bond by overlapping two orbitals, and those orbitals are going to contain electrons, let's start with two electrons, and let's start using the wave property of those electrons. So here might be one representation of an electron, and here might be another representation of an electron. These two electrons right now are perfectly in phase. Every peak aligns with every peak, every valley aligns with every valley. So to form a bond, we would overlap the orbitals containing these electrons using the linear combination. We would do so constructively and destructively. Constructively is like additively, where we take these two electrons and we put them perfectly in phase and we add them together perfectly in phase. We have constructive interference of these waves. Now, if we have two waves that are perfectly in phase and we add them together, what would happen to the amplitude of this wave as we add these two waves together? What would the resultant wave look like? It would look like the same frequency, but the amplitude would be bigger. As we add these together, every peak amplifies every peak, and every trough amplifies every trough, and we get an additive constructive interference of these two waves. So this is one part of the answer to the linear combination of atomic orbitals. The other part would come from the destructive or subtractive interference of these two waves. That's where we take these two waves and we make them perfectly out of phase with each other, where every peak aligns with every valley and every valley aligns with every peak. Now, if we take these waves and combine them, what would happen to the amplitude of the resultant wave when they are completely out of phase from each other? Every peak would cancel every valley would cancel every peak, and we would end up with just a straight, flat line. We would end up with a zero amplitude for that wave. We would call this a node. If all this sounds a little bit confusing, it's because it kind of is. We're boiling chemistry down to math. If you've ever heard, biology is applied chemistry, chemistry is applied physics, physics is applied math, everything boils down to math. This is looking at chemistry from a purely mathematical standpoint. It's a bit complicated. So I have another video where I go through this example with the hydrogen atom. That video is linked below, so you may want to check out that video next to see how the linear combination applies to something really practical like H2. So at its most base mathematic level, the bond is a combination of orbitals using the linear combination of atomic orbitals. That tells us that we have to add them together constructively, subtract them together destructively. We started with two electrons in two orbitals, so we have to end up with two new math equations. And these equations will describe the molecular orbitals that form. If orbitals are just answers to math equations, a bond is just an answer to what happens when you combine two math equations. And as we can see, that got a little bit complicated.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.